I will present you new heat exchanger models. As you already know from SimulationX 2024, we introduced the updated version of the heat exchangers that allows simulation of dynamic processes in heat exchangers and a little bit more numerically stable and allows to receive better performance in most of cases and still a good accuracy. I will start with simple heat exchangers, with the basic heat exchangers. You already know the versions for pneumatics and hydraulics, with pneumatics and hydraulics connections that can simulate gas or liquid. And in the new version, we also introduce a new heat exchanger with a two-phase flow simulation that allows to connect this heat exchanger with a thermofluidics library. This heat exchanger is a little bit different from the gas and liquid heat exchangers that we used in the first release. In the heat exchanger with the two-phase flow, we have a possibility to consider a discretization of a flow, because if we have some evaporation or condensation process in the heat exchanger, it makes sense to use a discretization. That's why we also enabled the discretization option also for simple heat exchanger with a two-phase flow. And the main feature of two-phase flow simulation in this heat exchanger that we simulate this process, the liquid and gas phase separately. If you go to the substructure of this heat exchanger, you can see that the basic elements that we use to simulate a two-phase flow are separated for gas on the one side and for liquid for another side. As you can see, we also extended the basic elements that we used in the past version, and that's why it brings also improvements also for the old models of heat exchangers. We updated the fluid properties calculation approach, implemented a real upwind method to calculate the fluid properties depending on the flow direction. That's why important information. It could be, you can see the different results also for old heat exchangers, but it should be really improvement. We will describe it in this documentation and release notes. Of course, we can also clarify this in the help desk and explain you in more details. But first, important information that improvements that we made for the basic elements has also influence on old heat exchanger model. So I will go forward. Now we are going to discretize heat exchanger models. You already know three models with one phase flow, and in the new version we introduce also three new models for two-phase flow calculation possibility for each interface correspondingly. For example, we have a version for two-phase flow on one side and liquid on another side with hydraulic interfaces and thermofluidics interfaces, with thermofluidics on one side and pneumatics on another side, and also the heat exchanger with the thermofluidics with a two-phase flow on both sides. Now I'd like to go to the demonstration model. We updated refrigeration cycle, the air conditioning cycle, and implemented the new heat exchangers. I must say that the new approach that we use in these models is very powerful and allows to simulate the separate flow, the flow and the two-phase flow separately for gas and liquid. And it's a really powerful thing. But another side, we are struggling now with some performance issues, especially with a CVOD solver. It will be a point for the further development to improve this, but already now we can achieve simulation time, a real-time factor bigger than 1 for refrigerating cycle. Let me explain the model at first. We have a typical refrigeration cycle with a compressor, with a condenser that we use to condensate fluid. So in this example, we use standard air 134A fluid, and then we reduce the pressure and then evaporate this liquid, and at the end we have a closed cycle. And another difference and another feature that we introduce in the heat exchanger is the possibility of considering humidity if you use a gas pneumatic connection on one side. For example, so if I will start animation, you can see that condenser side we use humid air to cool down two-phase fluid at the end. So we have a relative humidity 40% on the one side, and on another side, because of heating of the air, we have a reduced relative humidity. And on the evaporator side, we can see that if we cool down air with humidity, we can achieve the relative humidity above 100%. And in this case, heat exchanger consider condensate mass flow. That means that water that contained in air will condensate, and we can also calculate the mass flow of this. It also has influence on the mass flow balance. If we will analyze the mass flow on the outflow, of course, we will see that the mass flow is less than on input, because we take this condensate water from the system and consider the condensation process. And we hope it will also improve the user experience, so that user can also simulate humidity condensation. In a lot of cases, it totally makes sense to consider the humidity on the gas side.